In this video, we're going to begin looking at magnetism. We'll begin with observations of magnetism and then move to magnetic fields and magnetic forces. So first, let's look at a common bar magnet. A bar magnet has what we call a north pole and a south pole. If we bring another bar magnet in the same orientation near the first magnet, the south pole of one will be attracted to the north pole of the other. Then bringing them closer, this force of attraction will increase. And eventually, bringing the magnets close enough, the force will become very strong as the distance decreases, and the magnets will snap together. And now they will behave as though they're a single large bar magnet. If we take the second bar magnet and flip it around so that like poles of the magnets face each other, now they will repel one another. Pushing the magnets closer together, this repulsive force will start to increase. And eventually, bringing them very close will cause the force to be very strong. And this is something you can feel if you actually do this exercise. In fact, if the magnets are not perfectly aligned and we let go of the magnet on the right, it will begin to turn, and eventually it will align itself with the other magnet as before. So similar to electric charge, we have opposite poles that attract, just as opposite charges attract. And like poles repel, just like charges repel in electricity. We also notice that this force between magnets occurs at a distance without the magnet touching, just as with electric force between charges. So to explain this, we say magnets produce a magnetic field just as we said charges produce an electric field. The magnetic field lines go out of the North Pole and into the South Pole. So for a bar magnet, most of the field lines will bend around to form loops out of the North Pole and around back into the South Pole. We'll denote the magnetic field with a capital B, and since it has a value and a direction at every point in space, it is a vector field just like the electric field. Notice that we draw these field lines in loops rather than have them start at one pole and then truncate or end at the other pole. This is one of the key differences between electricity and magnetism. In electricity, we had single positive point charges, which we could call a positive electric monopole, where the field lines move away in all directions. We also get negative point charges, or negative electric monopoles, with field lines going toward the charge. We don't get these single poles in magnetism. There is no lonely magnetic north pole producing magnetic field lines outward in all directions. There is also no lonely magnetic south pole producing magnetic field lines inward in all directions. In other words, there are no magnetic monopoles. We have never found a magnetic monopole in nature and have never created one in the lab. Our current theories of electromagnetism assume magnetic monopoles cannot exist, and so far they are only studied as hypothetical particles that may exist under very special conditions, if at all. But if we look at our bar magnet from before, what happens if we just break our magnet in two, separating the north and south poles? Well, doing this just creates two smaller copies of the original magnet. We can explain why this occurs shortly. First, we'll look at another source of magnetism you may or may not know about. Say we have a wire, and all around the wire we place small compasses. A compass itself is like a small bar magnet with a north and south pole, which can pivot or rotate about a point at its center so that it can align with the magnetic field of the Earth. This means all of the compass needles around our wire will point north. But this only occurs when there is no current in the wire. When we turn on a current, in this case flowing up the wire, now all of the compass needles are deflected. And you may notice now they all point in a different direction that seems to rotate in a circle around the wire. So a current must produce a magnetic field that forms a circle around it. Since the magnetic field is moving in a plane that is perpendicular to the current in the wire, we need a convenient way of indicating the direction of quantities in 3 dimensions so that we don't require a high-quality perspective drawing to describe what's happening. So we will let the plane of the screen or paper, whatever you happen to be looking at, to contain 2 of our directions, say x and y, then a third z direction will point perpendicular to this xy plane. We will represent a quantity that has a direction into the page, or moving away from you, with an x. So a uniform magnetic field that is going into the page everywhere, we could represent with many x's that are evenly spaced. We will represent a quantity that has a direction out of the page, or out of the page toward your eyes, with a dot or small circle. And again, a magnetic field coming out of the page may be represented with many dots. And if we have current moving through a wire that we want to depict going into the page, we can draw a circle representing a cross-section of the wire and then place an X in the middle showing the current is going away from us. Similarly, we can draw a circle for the wire with a dot or smaller circle inside for current coming out of the page. We can remember these by imagining an arrow. The point at the tip represents the dot, and the feathers or the wings at the tail represent the X's. If the arrow is coming out of the page toward you, you can imagine you would be looking at its tip or the dot, while if the arrow was moving away from you, you would see a cross or X formed by the wings. Now we can draw a wire carrying current going into the page. This will create magnetic field lines that form circles around the wire. And you can imagine the field will decrease or weaken as you move further away. Also, notice we've drawn the magnetic field going clockwise in this case, rather than counterclockwise. This is on purpose, and we'll see why in a second. So now we have seen two sources of magnetic fields: permanent magnets, such as bar magnets, which seem to always create magnetic fields, and moving charges, which we call electric current. And it turns out these are not two different sources, but they are really the same thing. If we take a bar magnet and we zoom into the atoms making up the magnet, we will see many atoms where electrons are orbiting positive nuclei. These electrons are moving charges, so they are each creating a small magnetic field. And when all or most of the atoms have electrons that spin in the same direction and create magnetic fields in the same direction, all of those tiny magnetic fields add together and give a larger macroscopic magnetic field of the bar magnet. In reality, the small magnetic fields don't all perfectly align, and some are pointing in seemingly random directions. But if they have a net field in some direction, then the object is magnetic. The more atoms are aligned, the stronger the magnet will be, and some materials do this easier than others. Some materials are not magnetic on their own, but the small magnetic fields inside the material will align with external magnetic fields, and when this happens, we say the object has been magnetized. So now let's look at the math that we use to quantify magnetic fields. We'll begin looking at the field produced by a single moving charge, similar to how we started with the electric field of a point charge in electricity. This magnitude of magnetic field is given by the Biot-Savart law. We measure the magnetic field in units of teslas, and 1 Tesla is equal to 1 Newton per amp per meter. The direction of the field we'll find using the right-hand rule, which we'll see in a second. This constant mu naught is called the permeability of free space, and it plays a similar role for magnetism as epsilon naught, the permittivity of free space, did for electricity. We can also write the Biot-Savart law in terms of a cross product. Here we have a charge q moving with velocity v. We want to find the magnetic field at some point that is indicated by the vector r, which points from the charge to the point where we want the field. To find the direction of the field, we use the right-hand rule. In this case, we point our fingers in the direction of the velocity of our charge. Then we curl our fingers in the direction of the vector r, pointing from the charge to where we want the field. And now our thumb points in the direction of the magnetic field at the point we're interested in. Just as with electricity, we're usually not interested in a single charge, but the effect of many charges, or in this case, many charges moving, which forms current in a wire. We can take the Biot-Savart law for the field of a small amount of charge moving through a small section of the wire, and then we can use our definition of current and solve for the small amount of charge moving through it in a given amount of time. This allows us to write the Biot-Savart law in terms of the current through some small section of the wire. To get the total field of the wire, we can just integrate over the length of the wire and account for the field generated by the entire current at all points along the wire. We won't do this integral, we'll just look at the result for some common fields we're interested in. First is the magnetic field of an infinite straight wire. The magnitude of this field is found using the following equation, and we can see the field drops off as we increase the distance r away from the wire. We're also interested in the field from loops of current formed by taking our wire and wrapping it into some number of n coils. The field inside this loop depends on n, the number of coils or complete turns made by the wire, as well as the radius capital R of the loops themselves, and of course the current. Finally, when we take many coils of wire, we form what is called a solenoid or a long coil, where the length is typically much greater than the radius of the individual loops. In this case, we describe the field in terms of the turn density, little n, which is just the number of turns per length of the solenoid. This is a special configuration where the magnetic field at the center of the solenoid is approximately uniform and approximately zero outside the solenoid. So in a way, a solenoid is to magnetism what a parallel plate capacitor is to electricity. Now notice the field of our current loop that we have shown in the middle. Let's compare this to the field we drew earlier for a bar magnet. If we rotate our current loop, we see it has the same shape field as the bar magnet, and therefore behaves like a magnetic dipole. This should be the case after all, since the field of a bar magnet is the result of many smaller current loops. Looking closer at a current loop, the field away from the center of the loop is a little more complicated. But if we look far enough away, at a distance much larger than the radius of the loop itself, we can use this approximation for the field of the loop. Notice that we can write the field in terms of the area of the loop. We will now define the area of the loop times the current to be the magnetic moment of the current loop. This will be a vector quantity that points from the south pole to the north pole and is analogous to the dipole moment we saw for an electric dipole in electricity. In the same way, electric dipoles show up in a lot of our analysis of electric charge. Magnetic moments show up quite often in our analysis of magnetic properties of materials. Remember, in electricity, we had Gauss's law, which was a convenient way to find the electric field of some continuous charge distribution, and we used it in cases of symmetry. Gauss's law was always true, but we used it when we could focus on problems that could be simplified by symmetry. In magnetism, we get a similar law called Ampere's law. Gauss's law is used to find the electric field, and Ampere's law is used to find the magnetic field. In Gauss's law, we needed to find the charge inside some closed imaginary Gaussian surface. And in Ampere's law, we need to find the current passing through some closed Amperian loop. We won't go into detail about Ampere's law here, just know that it is a way to find the magnetic field and is similar in nature to Gauss's law. Now that we have the magnetic field, we can finally look at how magnetic fields exert forces and interact with charges. If we have a uniform magnetic field going to the right, and a charge is placed in the field, it will not feel a force. If the charge begins moving in the same direction as the field, it will still not feel a force. However, if the charge is moving in a way that is some amount perpendicular to the field, then it will feel a force. This force will be perpendicular to both the magnetic field and the velocity. We saw a force moving parallel to the field feels no force, so the smaller the angle, the weaker the force becomes. As we increase the angle, the force increases and is maximum when the velocity is completely perpendicular to the field. We can write this force quantitatively as the charge times the cross product of the velocity with the magnetic field. Or if you're not familiar with cross products, the magnitude of this force is given by QVB times sine of the angle phi, where phi is the angle between the velocity and the magnetic field vectors when they're drawn from the same point. Then the direction can be found just by using the right-hand rule. Also, since the magnetic force is always perpendicular to the velocity, it only accelerates a charge by changing its direction. It will never change its speed. And since magnetic forces cannot change a charge's speed, this means magnetic forces do no work and do not increase the kinetic energy of charges. Now let's look at the circular motion of charges moving through a magnetic field. For charges to feel a force, they must be moving perpendicular to the magnetic field. The force the field exerts on the charge is perpendicular to the velocity. And since it is always perpendicular, this force causes a centripetal acceleration, which makes the charge move in a circle. Assuming the charge is moving at a 90-degree angle to the field, we can write the magnitude of this force as QVB and set it equal to the mass of the charge times the centripetal or radial acceleration, which gives mv squared over r. Now we can solve for a few different quantities. First, this circular motion is called cyclotron motion. We can solve our equation for the radius of cyclotron motion, which gives mv over q times b. If we want to know the speed v of a charge that's needed to maintain a certain cyclotron radius in a given field, we can solve for this too. And since we're going in a circle, it might be better to look at angular quantities. So dividing both sides by the radius gives the cyclotron's angular frequency. And finally, we can find the regular frequency in hertz by substituting 2 pi f for omega and solving for f. Now that we know how a charge behaves when it feels an electric force or magnetic force, let's look at a case where it feels both. We will create a uniform electric field using a parallel plate capacitor. In this case, the field will point downward from the positive plate to the negative plate. We will also create a uniform magnetic field that is pointing into the screen, which we'll indicate with X's. Now let's imagine a negative charge, like an electron, is moving to the right perpendicular to both of the fields. Since it is a negative charge, it will feel an electric force in the opposite direction of the electric field, which in this case is upward toward the positive plate. This force has a magnitude of Q times E. Using the right-hand rule, a positive charge would feel a magnetic force upward, so our negative charge will feel a magnetic force downward, and this force will have a magnitude of QVB. Now let's imagine the negative charge is moving slowly, so the magnetic force is smaller than the electric force. This will cause the charge to feel a net force upward and be deflected into the top plate. Now if the charge is going very fast, the magnetic force might be stronger, so the net force will be downward and the charge will be deflected into the bottom plate. So as long as we keep the electric field and magnetic field constant, there is a speed where the forces should balance each other and the charge will move straight through. Setting these forces equal to each other, we find the magnitude of the charge doesn't even matter, only the ratio of the electric field to the magnetic field. We call this device a velocity selector. By choosing the values of our electric field and magnetic field carefully, we can make a device where only particles with a specific velocity come out the other side. This is very useful for performing experiments and getting reliable results. We can also have the uniform magnetic field extend past where the plates and electric field end. When the charges exit with a specific speed, they will feel a radial acceleration from the magnetic force. If we choose to only fire particles with a specific charge, and they all come out with a specific speed like we just saw, the only thing that influences the size of the arc that they travel through will be the mass of the particle itself. This gives us a way to separate particles by their masses. The larger masses will have a larger cyclotron radius. So now we've seen a current-carrying wire produce a magnetic field, and we've seen moving charges feel a force from a magnetic field. So let's look at the force on a current-carrying wire. We'll place a wire vertically in a uniform external magnetic field that is oriented into the screen perpendicular to the wire. If current flows upward, then we imagine many positive charges moving upward, and by the right-hand rule, each charge will feel a force to the left, so the entire wire will be pulled to the left as well. If we swap the direction of current, now positive charges are moving downward, so the right-hand rule gives us a force in the opposite direction, or to the right. If we leave the current direction the same, but make the magnetic field point in the opposite direction, again the force will flip and be in the opposite direction or to the left. And finally, to look at the final case, we'll swap the direction of current again, and then get a force back to the right. With a few substitutions, we can show that the force felt by the wire depends on the current and the length of the wire, and of course the field strength. We can write this as a cross product, just as the force on a single charge, or get the magnitude just by multiplying by sine of phi. Now this is the force on a single current-carrying wire in an external magnetic field. But we know current-carrying wires produce a magnetic field of their own. So we can place two current-carrying wires next to each other, and they should interact with each other. But we will need to be careful not to mix them up. We'll begin with only a single wire on the left, and later place another wire to the right oriented in the same direction. The first wire will have a current moving upward, which we'll call I1. Since we are going to place the second wire to the right, we want to find the field it will produce on this side. Using the right-hand rule, we find the field will point into the screen, and we'll call this B1. Now we will place our second wire and have the current going in the same direction as the first. We'll label this I2 and use a different color to not mix them up. The second wire will also produce a field, but we will want this field on the left side, where the first wire is being placed. Using the right-hand rule, we find the field will be out of the screen toward us. Now we're ready to look at the forces. For the first wire, we'll use the right-hand rule to determine the force for current moving upward in a field that is out of the screen. The force will be perpendicular to both, and in this case point to the right. We'll call this the force of 2 on 1. The force on the second wire with the current moving up, but in a field in the opposite direction into the screen, the force is to the left, which we'll call F1 on 2. Here we can see that wires carrying current in the same direction will be attracted toward one another. Combining our equations for the force on a wire and the field produced by a wire, we get the magnitude of this force. Now we can see what happens if we flip one of the current directions. If we only change the current direction in the second wire, it will feel a force in the opposite direction. But this also changes the direction of the field interacting with the first wire, so its force gets flipped as well. This means wires with current in opposite directions repel each other, and the magnitude of this force is the same as before. Now let's replace our straight current carrying wire with a current loop in a magnetic field. Imagine a loop lying in the XY plane and its area facing along the z-axis. Then we'll rotate the loop at an angle theta about the x-axis. We'll say the loop has current going around counterclockwise if you look down the z-axis. Now we will have a uniform magnetic field pointing in the positive z direction. If we look at each side of the loop individually, we can use the right-hand rule to find the direction of the force on each side. The two sides that run through the x-axis will have forces in opposite directions and will cancel each other out. The top and bottom will have forces in opposite directions, but they are not directly opposite. There is some perpendicular distance between the force vectors. This pair of forces form what is called a couple, which will act to rotate the loop, in this case about the x-axis. The torque of this couple is given by the force times the perpendicular distance between the two forces in the couple. The torque can also be found by using the force times the moment arm, or perpendicular distance to the x-axis in this case. And then we can double it since there are two of these forces. After doing some substitutions, we can write this torque in terms of the magnetic moment of the loop. In treating the magnetic moment as a vector, we can write this torque as a cross product of the magnetic moment and the magnetic field. This will cause the loop to rotate until the plane of the loop rests in the XY plane. Now the forces on the top and bottom edges of the loop are directly opposite and cancel. This is a very important example because it gives us the start of an electric motor. We can use two large magnets to produce a uniform magnetic field between them. Then we place a current loop in this magnetic field. The loop is connected to a voltage source at its ends to drive a current. The loop will begin to turn as it feels a torque from the magnetic field. But the loop will not simply stop once it is aligned with the field. Its angular momentum will cause it to overshoot a little bit, which we didn't point out in the previous example. At this point, the loop would typically feel a torque in the opposite direction and then begin to oscillate back and forth before stopping with its face aligned with the field. However, the loop is connected to its voltage source by a slip ring, and every time the loop completes half of a turn, the ends of the loop make contact with the opposite terminals. This causes the current to flow through the loop in opposite directions and changes the direction of the forces and thus the torque on the edges of the current loop. Now the loop will speed up just after it overshoots as it tries to align its face with the opposite direction. But then the current changes directions again, so the loop will keep spinning. Now we are able to rotate an object using electricity and magnetism. And this allows us to use electrical energy to move objects and do work. We will talk about the opposite of an electric motor, which is a generator and works in a similar way but in opposite directions. For a motor, we use electricity to move things. And in a generator, we move things in order to generate electricity. And for that, we'll need to look at electromagnetic induction, which we'll do in the next video. So that's it for this video, and I'll see you in the next one.